Hi everyone, and welcome to this overview video of the B200 clock. On the left hand side we've got the bottom enclosure with the stepper motor connected and this little needle over here and the distance sensor there to detect when this needle passes over. We've got the stepper controller board down here, and then the primary logic controller board up here. So the stepper controller board is primarily responsible for controlling the stepper motor using the Excel stepper Arduino library. We've got a normal Nano installed down here, and this essentially will only run the stepper motor, not much else. And we dedicate all the computational resources for the stepper motor to get a nice smooth continuous motion of the stepper motor with the stepper driver over here, filtering caps over there, and all the connections over on the left hand side. To power everything, we've got a 12 volt connection DC coming in. We've also got an optional battery connector over here, and there's automatic switchover happening between the 12 volt DC and the battery connector. If we connect 12 volt, this will pull the relay high, and it'll connect that power connection into the power regulator down here, the 12 volt below the regulator. If there is no external power source, there's the optional battery connection over here, and that will connect as soon as the DC power is disconnected. The relay will fall back down to the common position, and the battery will be connected to the system to power it. And the relay switch is quite fast. We've got a selection of filtering caps distributed around, so those few milliseconds that the switchover happens, there's still enough charge in the system to keep it going up until the new power source is connected. So the 12 volt regulator gives power to the system, including the stepper motor, as well as the 12 volt passing through up here to the logic control board. We've got a Arduino Nano 33 IoT running up here, so for all the logic to control the sensors, the interface, LED ring, as well as communicating with the Nano down here using a serial connection, connecting the two boards together. And ultimately this one will sit in the top enclosure, this one in the bottom enclosure of the clock, and that's how we transfer information. We can also read things like the battery voltage down here, can be sent up to the logic controller board, as well as temperature measurements and brightness control that we can set for the LED ring. Minimizes wiring overheads and requirements to pull the wiring through in the final clock, especially the half meter roundabout that it'll sit tall. So let's get it all powered up. I've got my 12 volt DC connector plug over here. I've got the battery already connected, and the power switch is currently in the off position, so don't expect much to happen. I'm going to connect the 12 volt connection, and you would have heard the relay click on due to the DC power connector, and the LiPo charger also charging the lithium battery over here. And this is driven with a 5 volt regulator, so take 12 volts, take it down to 5, and the battery regulator and charger is happy, as well as the regulator down here that boosts anything from 3 volts up to 12 volts. Alright, so when I turn the unit on, you're going to see the stepper motor activate, and it's going to start its calibration sequence, which we'll get into more details in another video. So as soon as we power that on, you can see the Nano's up and running, see some LED indicators, and the needle doing its thing. So currently, this is running the calibration procedure, but just to keep it simple, I'm going to cover the distance sensor, and you'll see that the calibration sequence continues on with its process. While we wait for that to stabilize, you can also see the LED ring all lit up, and for the different types of modes on the display. Currently it's in pressure mode. If you want to change settings, we've got the gesture sensor up there, and if we were to control it with the direction right, there we go, you'll see that the menu also updates accordingly. If we do the motion correctly, there we go. There's the date, there's the time, and some other details as well. If we move all the way up to things like there's the normal sensors, we've got altitude, we've got the temperature, and currently we won't have any additional information coming down like the battery voltage from this unit, as the calibration procedure is currently still running. So while we can see the LED blinking with the logic controller requesting information from the stepper controller, she's still finishing up the calibration procedure, which is nearly complete. and you'll see it slows down once the needle crosses the threshold, and then we know exactly where the 0 point will be on the final calibration process. So right now you'll see the receiver and transmission LED blinking as the instructions comes in through the serial. Still the calibration procedure is finishing up. Just make sure that that is happiness all the way. And that should finish soon. So this is to set the homing position, find exactly where the 0 point is of the final disc assembly. So this will move down on the screw thread up until it roundabout touches this part over here with the magnetic clutch to ensure that they slip, so there's no over torquing or stripping of the threads or anything like that, or loosening it out of its housing. Everything is accounted for that way. And the distance sensor is dual purpose, so we can see the disc assembly moving up and down, and then the needle position as well. We can determine exactly when that crosses. So if the disc assembly is up quite a distance further than the 50 millimeters detection distance, you'll see a square output signal every time the needle crosses said sensor, whereas if the hard drive assembly sits down below, it'll just be continuously blocked. So that's how we can distinguish between these two states of where the disk assembly will ultimately end up. And right now it's currently trying to calibrate itself to go to the specific homing position, and there you'll see the data is received from the logic controller board. Every time that LED flickers, new data is being sent through. And now on the display we can see it's currently 4.25 volts for the battery voltage since it's being charged. And to show the functionality, what happens if the DC power plug is disconnected, we'll disconnect that, the relay falls down, connects the battery, and we'll see the battery voltage is now down to 3.35 volts, so around about 70% charged. You can also see the LED indicator here for the LiPo charger. So all in all, the unit pulls about 4.5 watt in its current mode. That's without the LED ring being accounted for. So that's another 1 or 2 watt at around about 20% brightness in this case. So really very conservative on the power requirements. So on the stepper motor driver, we lowered the VREF to 0.6 volt, and that reduces the current roundabout to 1 amp maximum, because we don't need a lot of torque for the system to function, and we don't need to waste unnecessary power as part of the battery backup system either. So this is just a quick overview to show all the hardware capabilities. Everything's working well this far. We've got all the sensors hooked up using the quick connector system for I2C protocol. And once we get the final 3D printed units, we'll start assembling the entire clock, integrating all of the electronics, and just neatening up the wiring as well. Alright, that's it from me. Until the next video, thanks for watching.